Well, in the previous lesson, in the previous hour, we have discussed how to find electric field intensity of the electromagnetic wave from the magnetic field intensity. Okay, I think it is not so difficult. It was easy. And now another example. Try to do this exercise by yourself. Just read the question and try to do this exercise by yourself. All you need to do is to show that the following two forms of intrinsic impedances, first this form and this form, are identical. They should be identical. Okay, try to do this.
So'z keltirib chiqaramizmi buni?
Yes. You need to derive one expression from another. Well, it's not so difficult. You may do it in 1 minute or 2 minutes.
Okay, bilan. So'z birida ikkinchisini keltirib chiqarish kerakmidi?
Yes.
Bo'ldim.
Okay, one moment. So, what have you done?
Ko'rsataymi ustoz?
Yes. I will.
Birinchi buni
Can you
birinchi
look? Can you share your screen?
kompyuterda ko'rsataymi. Hozir.
Just share your screen. And did you write on the PC or on the copybook?
Men daftarga yozuvdim.
Okay. No problem. In that case, let's.
To'xtab turing ustoz, share qilaman. Hozir ulab olay.
Okay.
Razрешить berib yuboring endi. Ustoz uni ruxsat berib yuborish fikringa.
Menga kelgani yo'q. Okay. Well, I will show very quickly. Eta is given as omega mu over k, and we know that k is equal to omega square root of mu epsilon. We put this expression here. What we get? Omega multiplied by mu over omega square root of mu epsilon. What we get is okay, omega simplifies, square root of mu and mu simplifies. What we get is mu over epsilon, and if we where are my tools? And what can we do is so we take mu over epsilon and we multiply by k, divide by k, and so let's write mu epsilon multiplied. K is omega square root of mu epsilon over omega square root of mu epsilon. Okay. So this one is equal to k, and What about the denominator? Square root of mu simplifies. Square root of epsilon multiplied square root of epsilon gives us epsilon. And we get k over omega epsilon, which is equal to omega mu over k, which is equal to eta. So this was simple. Okay. Now we have a bit of theory about how we can generate the plane waves, and also a bit of theory about electromagnetic spectrum. So now we know how to write electric field from magnetic field, or vice versa. We know how to write a magnetic field from electric field. And now it is we may return to the beginning and discuss the idea of plane wave and its generation. So the idea of plane wave and its generation. So suppose that we have built an infinite sheet of current with a total line current density of Js. So suppose that we have an infinite sheet with infinite sheet. Let's say this is the side view of our sheet, infinite sheet with total line current density of Js. And here in this figure we may see how can we get the infinite sheet with a line current density of Js. In order to do this, we may use a stack of infinite wires. So infinite wires are stacked one onto another, and in this principle we may get an infinite sheet with a total line current density of Js. Okay, if current is an AC current, if the current is an AC current, then a wave generated then a wave is generated, which propagates away from the sheet of current. Well, if we let an AC current go through these stacked wires or a stack of infinite wires, And if we let AC current go through this stack of wires, electromagnetic wave is generated and is propagated away propagates away from our sheet our sheet. So the magnetic field intensities and electric field intensities can be computed from the Ampere's law, and in this case these are already computed, and electric field intensity is has uh, has a direction of has a direction in the negative x direction, and the magnetic field intensity on the right hand side of our sheet has a negative y direction, and on the right hand side, sorry, on the left hand side it has a negative y direction, and on the right hand side it has positive y direction. Okay, from Ampere's law, magnetic field intensity, which is H in our case, is is constant on any plane parallel to the sheet. Or it means okay, here we are taking the infinite sheet because of it is infinite on any plane which is parallel to our sheet. The magnetic field intensity will be constant. uh, okay, will be constant, and since in this case our sheet is perpendicular to the direction of propagation, we may conclude that we are generating a true plane wave. Well, of course, in of course, physically we are not able to perform this to perform this, uh, and that's why we cannot obtain a true plane wave in any physical application. Uh, everything that we are considering as plane wave is an approximation. Okay, now we have a bit theory about the electromagnetic spectrum. I think you have an idea of electromagnetic spectrum from the school. You should have an idea. Well, from our previous lessons, we can we can conclude that low frequency wave has uh, has a long wavelength, and a high frequency wave has a shorter wavelength. Well, this this fact is quite important in applications of electromagnetic waves. And for example, we may say that we know that low frequency sound uh, is able to propagate to larger distances. Okay, and if we look to the electromagnetic spectrum, or if we start to think about the electromagnetic waves different with different frequencies, uh, for example, TV transmissions uh, TV transmissions uh, can be made in the range of 54 megahertz up to 800 megahertz, or satellite communications are performed at frequencies from 1 gigahertz up to 30 gigahertz, or for example, a radar speed detector operates at a frequency of 10 gigahertz and 30 gigahertz, and so on. Uh, and so on. And as you can see, as you can understand, the electromagnetic spectrum is divided into various bands, various bands, based based either on either on frequencies or the equivalent wavelength. So if we look to the electromagnetic spectrum, or to this picture, we may note the followings. Of course, the electromagnetic waves are the frequency of electromagnetic waves is between 0 and infinity. Uh, in some in physical applications, we may not be able to use waves above certain frequency, but they do exist. Uh, the second note we can the second thing that can be noted is that infrared lights, visible lights, ultraviolet ultraviolet rays, X-rays, cosmic rays, and etc. are all electromagnetic waves. So this this is probably this is familiar to you from the school or from the college. Uh, the light, or for example, infrared light or ultraviolet, X-rays, or visible light uh, are electromagnetic waves. and the narrow bands below infrared, look here, This is the band between 0 hertz and 10 to 10 to the power of 12 hertz is shown in the second figure. Narrow bands below infrared band are arbitrarily divided by wavelengths and designated names. Here, here you may see the name of each band: ELF, SLF, ULF, VLF, uh, uh, which uh, which may stand, for example, LF low frequency, MF medium frequency, high frequency, very high frequency, ultra high frequency, uh, super high frequency, and extra high frequency. And on the left hand side is the same: very low frequency, ultra low frequency, uh, super low frequency, and extra low frequency. All this band, which is from 3 hertz up to up to 3 multiplied 10 to 12 hertz, is called radio spectrum. And the band between very high frequency and uh, the band between very high frequency and frequency of 3 at 3 multiplied 10 to 12 is called microwave bands. and and the band between 50 54 megahertz and up to 216 megahertz is called very high frequency channel allocation. And uh, here you may see from 88 up to 108 megahertz is reserved for FM radios. So reserved for FM radios. Uh, simply from the simply when you listen to the radio or when you choose the channels of radio, for example 101 FM or 102 FM, this simply means the frequency at which that radio station is broadcasting. Okay, in this course, in the course of electromagnetics, the most of our the most of the part of our work will have to do with the spectrum below the infrared region. Uh, because the much of the work in light in infrared, visible light, ultraviolet, X-rays, gamma rays uh, is treated in simply is treated in optics. Okay, we are interested in our course we are interested in this band. Okay, so what else? The electromagnetic spectrum in this figure shows, in addition to frequency ranges, some of the general applications. We have already seen this. As we mentioned above, for example, the uh, radar radar speed detection equipment, okay, which usually use police, is in the range of uh, is in the range of 10 gigahertz and uh, 30 gigahertz. Well, sometimes the frequency ranges, the frequency ranges which are used is allocated by convention. For example, the uh, if if you are if you are an if you are an amateur radio broadcaster, not commercial but amateur, you are broadcasting just for yourself and just for, okay, you are broadcasting just for yourself and just for fun. This band, allowed band for this kind of radio broadcasting is 3 point, from 3.5 up to 4 megahertz, for example. This is by convention. Of course, you may use other frequencies, but okay, the use of other fre- use of frequencies which are different from convention we can say is not good. Okay, I think this is all about okay, this is not all about electromagnetic spectrum, but this is the general idea about the electromagnetic spectrum. Okay.